Hi, I'm Dhruv, and welcome to my presentation on planning for complex non-prehensile manipulation among movable objects. I like to use this video to illustrate what I would like our robots to be capable of doing. If I want my robot to grab me my favorite can of beer from the back of a cluttered refrigerator shelf, the planning algorithm it's running must be able to reason about how to rearrange this clutter and all the configurations that these objects in the scene might end up in. This makes the planning problem difficult for two main reasons. The first is that with each movable object in the scene, the configurations that they take grows the number of states that the environment as a whole can be in combinatorially, and therefore it becomes really difficult to find a solution trajectory to retrieve the goal of this tomato soup can outlined in yellow. Secondly, because we're actively rearranging the scene, we need to reason about the effect of robot actions on the configurations of these objects. In our case, we do this by querying a computationally expensive physics-based simulator within the planning loop, which lets us compute nice solutions to complicated problems. However, if you do not have such a model, then you might run into undesired consequences, such as an object falling over in this case, or failing to achieve the goal grasp that you specified for the target object. So more formally, this problem of manipulation among movable objects requires our robot to grab and extract a target object from a cluttered shelf while satisfying all physics-based constraints related to these objects on whether we can make contact with them, whether we can make them tilt, topple, whatever the case may be. And from a planning perspective, it requires that these algorithms are capable of multi-step reasoning about which objects should be moved, where they might be moved, and how the robot can actually move them. In previous work, this problem has been simplified in two main ways. The first is to limit the robot to only using prehensile or pick-and-place style rearrangement actions, which from a planning perspective is much simpler because you can grab an object, it's now rigidly attached to your kinematic chain, and you can fall back to collision-free motion planning. Second simplification, which does allow non-prehensile rearrangements, limits them to a planar world where objects don't tilt or topple over, so finding pushes is much simpler. Our work is the first to address long horizon, multi-step, non-prehensile rearrangements in fully 3D workspaces where these objects can tilt, topple, lean on each other, slide, etc. We address the two main challenges with help from two insights that we draw on. So to address the fact that the search space explodes with the number of movable objects, we come up with this unconventional insight that we can think of these movable objects as tiny little robots themselves. So we artificially actuate them. And then we can construct an abstract multi-agent pathfinding problem where their goal is to get out of my robot arm's way. So the solution to this multi-agent planning problem is a robot arm grabbing the target object while the movable objects remove themselves from the robot arm's way. Given that we have this information, our second insight is that we can postpone simulations until absolutely necessary, and specifically that we can postpone simulations only for actions that take us towards our goal of grasping and extracting the target object that we care about. And then the algorithm that we present in this work essentially iterates between these two components until we have solved the problem. So at a high level, our M4M, or multi-agent pathfinding for manipulation among movable objects, starts with an initial robot trajectory that is computed in the absence of all movable objects. The volume that this trajectory encloses in 3D space, shown in gray here, defines what we call a negative goal region for our multi-agent solver. The negative goal region is essentially a condition that says, so long as there are no movable objects within me, the initial trajectory can be executed to retrieve the target object. So when we run our multi-agent solver, it might say that in this example, objects A and B need to vacate the negative goal region via these pink paths. And if they could truly move on their own, they would just remove themselves from the robot arm's way, and we'd be able to execute that initial trajectory to solve the task. However, since that's not possible in the real world, we take that information, feed it to our push planner, which has access to a simulator, and try to come up with pushes that achieve the same result. In this case, the blue movable object topples over into a red obstacle that is not allowed to be contacted, which leads to an invalid push, and we go back and try and sample a different push. In this case, successfully pushing the other blue object off to the left. And then we can go back to our multi-agent solver from a different scene solve a new multi-agent planning problem. In this case, only object P needs to move, and essentially keep running this loop. So the push for object P now succeeds. We're in a state where no more objects need to vacate this negative goal region, and we can terminate because no more rearrangements are required. And the solution trajectory then is just push an object A to the left, come back and push object B to the right. And now you have made up enough space to retrieve that target yellow object. So I'll leave a bunch of these videos playing that show some real-world experiments that we ran on a PR2 robot in the lab, and some simulated experiments as well below. The important thing to note about our work is that we don't put any restrictions on how many objects a particular push can move, whether objects can move other objects. All of these are generalizable because the algorithm will find solutions where it pushes multiple objects at the same time, or an object pushes another object to clear up enough room. And there's a lot more quantitative results in our paper as well. So thank you for your attention.